In this video, we're going to resolve an improper integral in the case where the limit is more easily evaluated using L'Hopital's rule. So the integral that we have is the integral from 1 to infinity of x minus 1 e to the negative x dx. So I'm going to go ahead and rewrite my integral. So we have the integral from 1 to infinity of x minus 1 e to the minus x dx equals, we have infinity here in our limits of integration, so we're going to replace this with a limit. We're going to take the limit as a goes to infinity of the integral from 1 to a of x minus 1 e to the minus x dx. And in this case, this is going to be an integration by parts, and we'll let u equal x minus 1, which will make u prime equal 1. And we'll let v prime equal e to the opposite of x, which will make v equal the opposite of e to the opposite of x when we integrate e to the opposite of x. So we'll go ahead and do our substitutions in for our pieces. So I'm going to get the limit as a goes to infinity times, so integration by parts says take u times v, so we get x minus 1 times the opposite of e to the opposite of x. So there's a negative out front, and this part's already then been integrated, so we're running this from 1 to a, and then integration by parts says u times v minus the integral of u prime v. So we get 1 times the opposite of e to the opposite of x. So we get an opposite of e to the opposite of x. The minus can pull out. So we just get e to the opposite of x inside the integral, running from 1 to a dx. Close this off, closing this parentheses right here. And this, it looks like we can integrate. So this equals the limit as a goes to infinity of, just go ahead and distribute this 1 into the parentheses, so I get a 1 minus x. I have e to the opposite of x. We integrate e to the opposite of x, we get the opposite of e to the opposite of x. Take the derivative to check your work. Derivative of e to the opposite of x is e to the opposite of x. Then the chain rule says take the derivative of the opposite of x, which would be negative 1. And then when we bring that negative 1 down, it would convert this minus into the plus that we have here. And this whole shebang is going to be from 1 to a, all of the stuff on the inside. And we see that the e to the opposite of x can get factored out. There's more than one way to attack this one. Limit as a goes to infinity, that e to the opposite of x can factor out. That's going to leave behind a 1 minus x minus 1, and when this gets simplified, you see you just get the opposite of x, and this is from 1 to a. You want to recognize this as an indeterminate form. We'll take the easiest thing to do in this case is going to be to move the e to the opposite of the x down so that we get a positive exponent. We take the limit as a goes to infinity times, we have the opposite of x over, we move the e to the opposite of x down, which will change the sign on the exponent. This is running from 1 to a, and you want to look at the form of this. So the form of this, as a goes to infinity, e to the x goes to infinity, and as a goes to infinity, the opposite of x goes to the opposite of infinity. So right now I have the form that looks like this, the opposite of infinity over infinity, which is an indeterminate form to which L'Hopital's rule can be applied. So L'Hopital's rule says that this limit is the same as the limit applied to the derivative of the numerator over the derivative of the denominator. So we're going to take the limit as a goes to infinity of, take the derivative of the numerator, which is negative 1, over the derivative of the denominator, which is e to the x, and we're running this from 1 to a. And at this point, we're in a position to actually find the limit because we have a constant numerator, -1, and e to the x, as a goes to infinity, e to the x goes to infinity. So we have a constant over a denominator that's becoming infinitely large. So this ratio here, as a goes to infinity, is going to equal 0. Infinitely large denominator, a constant numerator.